Good morning, kids. Today's class we are going to discuss the electromagnetic induction in one shot. Once again, a very good, beautiful chapter. Very good concepts are there. There we'll be revising the total physics, even the mechanics, almost the waves and sound, all other topics you can revise here. Uh, For advanced, it's really, really very best chapter. For mains, okay, fine, it's a formula based. You should know all the basic concepts and formulas. It's a little bit lengthy chapter, quite advantageous. And what are the other chapters you must know? You must know the electrostatics, you must know the capacitor, current density, electromagnetism. If you know all these things, okay, fine, you can manage like this. It's an interlinked one. Okay, now what about the methodology, like how to prepare for mains advance with using this one shot? Watch like what all I'm teaching, watch it and learn what all the ideas, what all the different methods, skills I'm explaining. Learn it. Then you have to remember. Remember in the sense you have to recollect all. This is very important parameter for an exams, JEE mains and advanced. Remembering. You must be very good in recollection. Means how to remember things. The question comes by repetition, purely by revision. When you read this more number of times, 5, 6, 4 times, definitely you'll remember. Once you learn concepts and you remember formulas and ideas, solve P by Q. Then as you start solving problem, you will get confidence. With that confidence, what happen? You can do the higher level problems. It's like a slow learning process. All of a sudden, like this, I'll master electromagnetic induction. Not possible. You have to put hard work. This is very important at students' life. Don't believe in tricks, magic things. Believe in hard work. Definitely, you'll get a very good rank very easily. Fine. So we'll see that one. Next, how to plan this? How to prepare this one-shot EMI? Here I just proposing here electromagnetic induction one shot. First, you have to learn magnetic flux. Then, after learning magnetic flux, Faraday's law of electromagnetic induction. Two laws are there. So I'll explain the statement and formulas, everything. Then Lenz law to predict the direction of induced current. Then the Motional EMF. I think this will become your core 60% of the electromagnetic induction. Then next Motional EMF, one formula is there, how to use that one. Then rotational EMF. Then induced electric field. This is a little bit one independent topic and the conceptual. This is not interrelated to all. There's one independent topic is there. And the name electromagnetic induction, the chapter name comes because of this. There's a very good conceptual, beautiful topic. One, two formulas are there. If you remember formula, you can manage this. Then next inductance, growth and decay of current, self-inductance, RL circuit, all that related to inductance, that one. Then next mutual inductance, very, very, very important for mains advanced. After this Faraday's law, motions law, next weightage topic is mutual inductance. Always one objective. They never ask you advanced, high level. One objective. Means as usual, one simple formula based on mutual inductance. Advanced also formula based mutual inductance. The next LC oscillations. There's a, like you can say not very important. Just similar to SHM, all the formulas will apply for electrical oscillations. Then eddy current, no formulas are there, just a conceptual one. Important for mains as well as advanced, just a conceptual. Theoretical question they'll ask you. There's overall strategy for electromagnetic induction. So first learn concepts, very, very important. Clarity here. What do you mean by flux? What do you mean by motional EMF? You must know these things. Remember the suitable formulas, the derivations, all you must know. What is the meaning of them? Then next comes formula derivation. Next comes exam skills. You must, what do you mean by exam skills? Reading, question, the language, then search the idea involved, what chapter, what topic, what formula, and how to proceed with this. All this will come in examination skills. So you have to balance yourself. Examination skills will come by solving problem. Okay, fine. There's no equivalent to solving problem. First, reading, remembering, solving problem. These are the only three things will help you. Believe in this, you'll get good rank very, very easily. Any other thing, I don't know. As such, all my past 20 years, I'm saying all the students, they just follow this method, a simple reading, remembering, and solving problem. Put effort. Sir, how many problems per chapter? Means 50 problems is enough. You know, advanced is also around 50 or 50 ideas. That'll be enough that one. If you solve more number of problems, more better ideas. Okay, kids, now we'll start with the uh, next magnetic flux. I'll remove the camera because I don't have place to explain. Next, first the topic is the magnetic flux. Here we'll define this as flux is equal to magnetic flux equal to, the definition is B bar dot S bar. B is cos theta. BLB cos theta. Okay, this is a magnetic flux. The unit for this will be Weber. What is the theta? Theta is the angle between B bar and the area vector. Already we have seen in Gauss law. What is the n cap? N cap is the unit vector directed normal to the surface. So the further the angle will be BLB cos 0 degree. Then here n cap will be in this direction. So the angle between B bar and n cap, it is cos theta. So flux will be BS cos theta. Okay, these are magnetic flux. So there is some surface or loop. Like this we define. So what is the magnetic flux? It will give us information about the lines of force only. The magnetic field strength and the area. Okay, that particular thing, what we can call the product of that, we'll call magnetic flux. So magnetic flux, it will give us information. It will provide details of lines of force. Not more than this, not needed. Just have a small idea. This much will be sufficient. Next, we have the Faraday's law of electromagnetic induction. Faraday's first law of electromagnetic. What is the Faraday's first law? It says that the rate of change of flux is directly proportional to the EMF induced. Means the EMF induced is directly proportional to rate of change of flux. The negative sign is the induced EMF will oppose its own cause. Directly proportional to rate of change of magnetic flux through the circuit. Both are like a EMF. The Faraday's first law and second law combinedly we are expressing using this equation. So what is the first law? What is related? If a flux linking a loop changes with the time, it will produce EMF. Next, second law, what is telling? The EMF induced is directly proportional to rate of change of flux. Okay, there's about the Faraday's law. We'll take the convention. This is very important. I think somehow in the books you don't have in detail, so I brought it. So it will be very, very useful for you in solving problem. Because most of the students, they ask me like how to predict the direction of induced current. They have very simple, beautiful convention. I think in our books it is missing. In our books it is missing. I don't know what is the reason, but it's a very systematic convention available in some Western books. I just picked up. I'm just sharing it. In a region, if the magnetic field is into the plane, then the flux will be negative. If in a region the magnetic field is out of the plane, then the flux linking the region or flux linking the loop will be positive. Then Positive flux increases, d phi by dt positive. Positive flux decreases, d phi by dt negative. Negative flux increases, d phi by dt negative. Negative flux decreases, d phi by dt positive. Next again we have the E equal to minus d phi by dt equal to rate of change of flux. This is a Faraday's law. Substitute d phi by dt with sign. This is very important. Till here, okay, I think only you have to remember somehow this first one. Magnetic field into the plane of the loop, flux negative. Magnetic field out of the plane of loop, flux will be positive. Okay, with this. Then next we have this one. If after substituting d phi by dt, if EMF induced or induced current is negative, then it will be anti-clockwise. If induced current is positive, or induced current or induced EMF is positive, then the current flow will be clockwise. The induced current will flow clockwise in a loop. This is a basic convention. This I'll demonstrate here. We take help of this one. Here the bar magnet is a test. It is a test. No current here in the sense. This is about the Faraday's law. First we'll discuss about the now the lines of force which are there will pass through the coil and the magnetic field here will be constant. Okay, fine. Now I'll move the magnet. As I start moving the magnetic field linking the coil, there's a coil, there's a coil. The magnetic field linking the coil will change. Then according to the Lenz law, we'll just predict the current. You stand here, you are standing here. Then what you see, B bar into the plane, B bar is in this direction. You find little bit difficult, try to understand. 1-2 problems will get habituated. Then B bar will be along the axis of the coil. So according to this person, flux is negative. Then as you move bar magnet, the magnetic field strength in the coil will increase. So d phi by dt negative. If it is negative, then equal to minus d phi by dt. EMF induced positive. Okay, fine. So now, how the overall condition, EMF induced positive. Then the positive means how it should flow, the current should flow according to this person in such a direction, it should oppose. What is the Lenz law? The direction of induced current is such that it will oppose own cause. I'll go back, I think I missed statement. This is a statement. The direction of induced current is such that it will oppose its own cause. It will oppose its own cause. The direction of induced EMF is such that it opposes its own cause. There's a basic Lenz law. What do you mean by Lenz law means? There's a definition. Okay, kids, some correction here. If it is positive, I think. If induced EMF positive, then induced current will flow anti-clockwise. If induced EMF is negative, I think some negative, then it will flow clockwise. There's a basic convention. Please once again. Okay. Okay, we'll come back to this one. We have to apply the same Lenz law idea here. Here, so what is the EMF induced positive? Then according to this person should flow anti-clockwise. So the current here will flow anti-clockwise. In every loop, in every turn, the current will flow anti-clockwise. Okay, I think so. It's very simple. Faraday's law, Lenz law. Now we'll do one thing. There's again one more thing. The direction of induced current such that it will oppose on the cause. There's a north pole. Now this end of the coil will be north, this will be south. Why? Because the dipole moment of the coil will be in this direction. It should oppose it. And how the dipole moment will be from south to north. Then curl the fingers in the direction of current. Thumb will give direction of n cap, m bar. There's a basic idea. Similarly now, if I make this magnet to enter, we know how the B bar here will be in this direction. Who the bar magnet will produce. Then you are standing here. Then you see the B bar out of the plane. Out of the plane, flux will be positive. Then as you move bar magnet towards it, the B bar will increase. Flux will increase. d phi by dt is positive. If d phi by dt positive, the EMF induced will be negative. EMF induced negative means then E will be positive. EMF induced, flux is positive, EMF induced will be negative. Negative means how it should flow? It should flow in the clockwise direction. So for this person it will be clockwise. So therefore the current here will flow like this. There is a method to find out, okay, the current will flow like this here. Then what is this? This coil should oppose. How did it oppose? By making this end south, this is north. And the dipole moment of coil will be in this direction. Similarly, if the magnet is moved away, then the B bar still produced by bar magnet in the coil will be towards left. Now, as you move away the bar magnet, what is the flux? Flux will decrease. First, what is the flux? Flux as it is out of the plane. B bar is out of the plane according to this person. Here it will be out of the plane. So flux is positive. d phi by dt. As you move away, B bar will decrease. Positive flux decreases. d phi by dt negative. EMF induced positive. Then, so here, how the induced current should flow? If EMF induced positive, it should flow anti-clockwise. So it will flow like this. According to this person, you will see the plane of coil moving anti-clockwise. Okay, fine. Now, the direction of induced current should be such that it should oppose the cause. What is the cause? Magnet moving away. So it should be attracted. So therefore, this end will become north, south. The dipole moment of the coil will be in this direction. There will be attractive force on the bar magnet. Here there will be repulsive force on the bar magnet. Okay, we'll take the once again the Lenz law, the demonstration. Here the bar magnet is, you can see clearly, this is a person now. You see the flux into the plane, B bar into the plane, so flux negative. Negative flux increases, d phi by dt, negative. EMF induced will be positive. Positive means how the current should flow. Positive means the current should flow anti-clockwise. So according to this person, it should flow anti-clockwise means it will be like this, in this direction. Then the dipole momentum of the loop will be in this direction. Then this will become north, this will become south. So it will oppose. There will be repulsive force on the bar magnet. Then if it is a test, flux is rate of change of flux will be 0. So no EMF, no current. Then if you move the bar magnet away from it, here what is the flux? Flux is negative. Negative flux decreases d phi by dt positive. EMF induced negative. EMF induced negative means the current should flow in clockwise. Huh? So according to this person, the current will flow in this direction. You can see in opposite direction. Lenz law, you need this convention. Huh? Then here it should be like a what it do, it will try to attract. So this end of the loop will become south, north. Dipole momentum of loop will like this. There will be attractive force will act on the ball magnet. Similarly, under gravity, the weight mg of the bar magnet will act. Then this person will see that flux is coming out of the loop. So what is the flux? Flux will be positive. d phi by dt will be positive. This person is below the ring, d phi by dt positive. EMF induced. EMF induced will be negative. EMF induced negative means this person, according to him, it should flow in clockwise. Anti-clockwise will be positive. I'll indicate with the red color. This is the direction of induced current. Then M bar will be like this. So this end will become south, this will become north. So there will be a repulsive force. The direction of induced current is such that it should oppose the cause. A current flowing ring will behave like a bar magnet. Then the dipole moment, then north and south. Similarly, here we can see like this person, what should be coming from him? Flux will be positive. Positive flux now decreases. d phi by dt, negative. EMF induced positive. For this person, it should be anti-clockwise. So the current will flow like this. Then here, this will be M bar. This will be north and this will be south. Okay, agree this. Then this will be the attractive force. This will be weight will act here. So what is the acceleration? Will be less than g. What is the acceleration? Will be less than g. No. If a increasing current is flowing, what about the induced current in this particular loop? Now how this long wire, it will produce magnetic field here in this direction. Then the positive flux here, the flux will be negative. Flux will be negative. Negative flux increases. d phi by dt negative. EMF induced positive. EMF induced positive means then the current should flow anti-clockwise. This is a method. Okay, fine. Then if current, this wire is fixed, will move the loop away. Then what is the magnetic field due to this wire? D bar into the plane. Flux will be negative. As you move away, d phi by dt, negative flux decreases. d phi by dt positive. EMF induced negative. Then induced current will flow clockwise. Got the idea? This one? Okay, we'll take the next condition. Just I'm giving all examples, Faraday's law as well as Lenz law. We have the loop, there's a metal loop or ring of radius A, resistance R. Then as it starts rotating about a vertical axis passing through its center, then what about the flux? Flux is equal to B bar dot S bar ds cos theta. d phi by dt ds omega t. Okay, this is the EMF induced. Then what is the current? This is the expression for current. Fine. So the induced current, how the induced current will flow based on this particular thing. Again, same Lenz law, you can apply it. Next condition. Now here there is a rod. I'm going to slide it. So let this be the distance x. Magnetic field into the plane. So flux is equal to B into flux equal to B into A, L into X. So d phi by dt equal to what about induced current? Okay, that's about the Faraday's law, rate of change of flux equal to EMF induced. Then, now what about the induced current? So what is the flux? Flux will be, what is the flux? Flux is negative. Negative flux increases, d phi by t negative. EMF induced positive. So the induced current will flow like this. Then the induced current is subject to, it should oppose the cause. What is the cause? The velocity. So a BIL force will act according to the Fleming's left-hand rule. BIL force will act. What is the cause? This is the cause. What is the effect? What is the opposition? This BIL is opposition. Okay, fine. Next again, look at the here. B bar flux is negative. Negative flux increases d phi by t negative. EMF induced positive. Then what is I is equal to E by R. Then we will, how the current here will flow anti-clockwise. Simple. EMF positive, current anti-clockwise. EMF negative, current will be clockwise. Induced current. Then what about the from Faraday's law? E is equal to d phi by dt equal to pi r square there is a EMF induced. What about induced current? E by R. This will behave like a cell now. Next idea. There's a ring. There's a ring. I'll pull this ring from the magnetic field. For that, how much of charge will pass through it? So what is I is equal to E by R? What is I is equal to dq by dt? What is E is equal to d phi by dt? change in flux. What is the flux linking here? Final flux minus initial flux by radius. Final, this is a final. This is initial. Final flux, 0. Initial flux, pi r square pi a square b. So how much of charge will flow? This much of charge will pass through the ring. We have the next topic, motional EMF. So I have the metal rod, which is at rest. Then there won't be any EMF induced. As I start moving this rod, then the free electron which is present here will experience a force like a magnetic force B bar and velocity. The magnetic force on it will be downward. As a result of this, the electrons will come and get deposited here. And the deficiency of electrons here will create a positive charge. Okay, fine. And this will be moving. Then it continuously next further what will happen to electron means further like this the drifting of electrons will take place. How long it will take place till because this like electrons will get deposited. No, it will produce an electric field here. Then the electron which is present here the electron which is present. What is this? There is a field produced by the electric charges. So deficiency of electrons here, positive charge, absence of electrons here, negative charge. Okay, there is a negative here, electron which is present here. Now we'll experience a force, one electrostatic force. I'll remove this line, this is better for us. Okay, now the electron which is present here will experience an electrostatic force like this. And the magnetic force will be in this downward direction. How long? Why this electrostatic force? Because as the rod starts moving, the electrons will drift downward, will get deposited here. Efficiency of electron, here deficiency of electron will lead to positive charge. Okay, like this here we'll get the electric field vector here like a electrostatic force will be acting on the electron upward and the magnetic force will be acting downward. At one instant when electrostatic force balances magnetic force, no more drifting of charges and it will be at rest. The number of electrons here will be fixed, number of positive charges, a potential difference is set up across the rod. And this is called like a induced EMF. Okay, at equilibrium, Fe equal to Fb. F is equal to QE, this is equal to QBB. E equal to, there is a velocity here, B into B. What is E is equal to dE by dL, B into B. So E equal to VBL or BLV. In the vector form, we can write it as B bar cross B bar dot L bar. This is in a vector form. Now this is in a vector form, it will be like this, B bar cross B bar dot L bar. This is the induced EMF or motional EMF. Okay, like this, we are bringing up very, very important. Almost 80% of problems in electromagnetic induction are based on this. Very, very, very important. Okay, kids, now we'll go for the application part. So why do this EMF induce? Due to metal rod moving in a magnetic field. Okay, then we'll put some conditions. So what do you mean by L bar, effective length? Here, so in front of you, one straight rod, semicircular rod, and some zigzag and V-shaped rod. Let L be the length. They are sliding. I'll give number 1, 2, 3, 4. Then all this will be like a cell. So what is the EMF induced in all these four structures? Will be BLV only. Because all the velocity vector will be perpendicular to B bar. Angle between V bar and B bar is 90. So VB sin 90 VB. And that V bar cross B bar will be parallel to L bar. So the motional EMF will be BLV. Agreed? Like this. So this moving rod now you can replace with a cell. So where all this rod moving in a magnetic field, if you come across, so what you can do, you can replace them with a cell. Okay, this is motional EMF. Okay, like this we define the motional EMF. Fine. Now next, there is a L-shaped rod. We have to calculate the EMF induced. You can see the component of velocity. One, we'll discuss some cases. If there is a rod is there. If velocity like this, and B bar into the plane. What is the EMF induced? BLB. For the same rod, if the velocity is like this, making an angle theta, then it will have two components. One component V sin theta, other V cos theta. Who will induce EMF? Only component perpendicular to the rod, BL V sin theta. There won't be any EMF due to V cos theta. Similarly, for this rod, okay, it's having this L-shaped rod. It's having two components, one Vx, other will be Vy. Like this will be theta. There will be no EMF induced due to V cos theta. Only the velocity or so only the component perpendicular to the rod will induce EMF. This is a simple concept to remember like this. Then here this rod is there. EMF induced in the part, we have the part no? 1, 2 and 3. EMF induced in 1, 3 is given by B Vx into B. EMF induced in the rod, I'll write it here. EMF induced in the rod is equal to B Vx B. EMF induced in the rod 3 2 will be B Vy into A. Okay, how to decide which end is positive negative? Again the positive like this end will be positive negative. How to decide? Particular direction of EMF induced, or you can go for the simpler. A positive charge present will deflect upward, no? Similarly, this end will be positive, this will be negative. A positive charge, inside here we assume a positive charge. Then it's having a velocity, Vx. Then the magnetic force will act upward. So the positive charge will go deposit here, negative charge here. Similarly for this, you assume a positive charge here. Positive charge and velocity. So this end will become positive, this will be negative. So this will behave like a cell. Okay, fine. So then net EMF induced 1, 3. This is 1, 2, 3. E1, E2, 3. Add up these two. B VXB plus okay, this is EMF induced. Like this, these questions are very important. Now, at T equals 0, the rod is given. These are rails, conducting rails. Metal rails. The rod is given velocity V. The flux here is negative flux. Then negative flux increases d phi by dt, negative. EMF induced positive. Then the induced current here will flow anti-clockwise. Then the BIL force will act here. It will undergo retardation. Then what is the formula? We'll write it. MA equal to minus BIL. Then the moving rod will behave like a cell. This diagram I'll give, it's very important. I'm giving one diagram. This is the conceptual part of the diagram. The moving rod only will treat like a cell. The induced current then BIL force will act here. This will undergo retardation. The moving rod will be like a cell. The EMF induced equal to BL it is. Then what is the expression for I? I is equal to E by R, BLV by R. Substitute on solve, we'll get velocity V is equal to BL U by R e to power of minus lambda t, where lambda is equal to B square L square by MR. Lenz law, Faraday, everything is applied. So why this EMF induced? Due to rate of change of flux. Why flux is changing? Area is changing. B is constant. We take the next situation. Now the rod is pulled with a constant force F naught. Then again, what is the flux? Flux linking. Again, the moving rod will behave like a cell. After some time, so we can bring that cell concept here. Here only let me introduce. Why to draw one more diagram. The moving rod will behave like a cell. So how you give direction of induced EMF? First, what is the flux? Flux negative. d phi by dt negative. EMF induced positive. The current I will flow like this. Then this end will be positive, this will be negative. Therefore, it will be like this. So the induced current I will flow like this. Okay, fine. So now, what is the formula? Here it will be like a F naught BIL equal to MA. Then I is equal to E by R, BLV by R. Then A equal to dV by dt. Solving this, I'll get expression for velocity. The expression for velocity will be F naught R by B square L square lambda as usual B square L square by MR. Then what is the power? Power delivered external agent, power equal to F naught into V. And what was the power delivered? A part will be converted into kinetic energy of the rod. Remaining will be power dissipated in the resistor R. So power generated. Let me write that power equation. Power generated external agent equal to rate of change of kinetic energy plus I square R. Now rod pulled with a constant velocity node. The moving rod will behave like a cell. Already we have discussed this. The concept like this will apply it. So the rod will, after some time, will come to the next position. The moving rod only will behave like a cell. Then here in this region we'll call 192. In the region 1, the flux will be negative. Negative flux increases d phi 1 by dt negative. EMF induced positive. Then the induced current here will flow like this. In this region, flux is negative. Negative. EMF induced negative flux. Negative flux decreases, d phi by d2 will be positive. Here as the rod moves, the flux will decrease. So rate of change of flux will be positive, EMF induced negative. Then how the current will flow like this. Here I1 plus I2. The net current, let it be I. How BL flows will act here. The velocity V naught like this. For this we should apply the external force. The rod is also having internal resistance. So the overall circuit will be R1 RE R2 E by R plus R1 R2 this is expression for current. Okay, from where this R is come? Internal resistance of the rod. No. There is a cell switched on. First, when you switch on, current will start flowing. There's the initial, let it be as it is. The next part of the circuit. Now the current starts flowing. This current will flow I1. Just after the cell is switched on, current will flow. I1. Then BI1L force will act. It starts accelerating. As it starts accelerating, it will acquire velocity. Then it will behave like a cell. Then the current, induced current will flow. Now why induced current? Again the same thing, flux negative. d phi by dt negative. EMF induced positive. So the current, induced current, I2 should flow anti-clockwise. But I2 will be less than I1. So the resultant current, how it will flow clockwise only. There is a moving rod and its resistance is R. The resultant current here will flow like this. So this is BIL. No, like this, if a cell is there, okay, there's a method you can apply. Then this BIL will accelerate it. Then what is I is equal to E minus E by R equal to M dV by dt. Then this is E solving for velocity. Okay, agreed. Huh? Next we have the Motional EMF of cell with gravity. This rod is allowed to fall freely. So if the cell is switched on, this is allowed to fall freely. So weight mg will act. Then here I1 current will flow. After some time, current I1 will flow. I1 will flow. Then flux here will be negative. Negative flux. B bar into the plane, flux negative. Negative flux increases. d phi by dt. Negative. EMF induced positive. Then now the induced current should flow anti-clockwise. So here I'll show the direction of induced current. The resultant current will be in this direction. Then now BIL force, B bar like this, B bar into the plane current. So the resultant force will be downward. So here two forces acting. Actually, shall I tell you BI1L? BI1L will act here. BI2L will act upward. But I1 will be greater than I2 initially. So what actually happens here? Mg plus BI1L minus BI2L equal to ME, or Mg plus BL I1 minus I2 equal to ME. What is I1? I1 will be E by R. This will be BLV by R. Then M dV by dt. Then solving for it. So this moving rod will be like a cell. Somewhere here we can show like this. What is this? This is the EMF, applied EMF. This is induced EMF. The rod is moving like this. The net BIL will be like this. Velocity will be downward. Okay, fine. We have the capacitor. Okay, now as we know, the moving rod will behave like a cell. So this rod only will replace with a cell. Okay, this will be EMF induced D. Flux here will be negative. d phi by dt, negative flux in d phi by dt positive. EMF induced positive. EMF induced positive means the induced current should flow anti-clockwise. Then BIL force will act like this. The rod is having mass m. Then for that we should apply some external force also. Then what about current I? Then we know first what is EMF induced, motional EMF, BLV. Charge across capacitor, Q minus Q. The induced current will flow like this. So what is a charge across capacitor? C into E. C dl v. dq by dt. Then F external minus BIL equal to MA naught. This is A naught. Huh? So you have to pull up with this much of velocity. So when capacitor comes, current will be function of acceleration. When resistor comes, current will be function of velocity. These are small ideas, try to remember. Next we have the motional EMF with the rod and with capacitor and the resistor. The rod is pulled here. Where is the rod? This is the rod. It's pulled with a constant acceleration A naught. Then what are the conditions? Then moving rod will behave like a cell. So here we should replace this as a cell. Okay, this is a velocity V. The same rod only, this EMF V. The induced current. Sir, how you decide that induced current will flow anti-clockwise? Flux, negative. Negative flux increases. d phi by dt negative. EMF induced positive. So the induced current will flow anti-clockwise. Plus Q minus Q. Then two currents will flow. What about the here current? Current here actually two things are there. This will be I1. Then there will be also induced EMF here. What is the flux here? This flux will be negative. Negative flux decreases. d phi by d2 positive. EMF induced negative. Then here this current will flow like that. Altogether E equal to BL with happen. So now what is the current? I1 is equal to E by C. What is I2 is equal to E by R. What is BL? V it is. I2 equal to BL V by R. What is V equal to? A naught into T. What is the total current? I is equal to I1 plus I2. Can you write like this? I think this is anybody wants to question me, like you can't, of course you can't question, but see that current equal to EMF by resistance, okay, but current is not equal to E by C. There's some issues there. So what is the method actually? Here I1, how will bring it? I1 will bring it in this way. Charge equal to C into E. Or further this is BLV. Then differentiating A naught. So this will become CBL A naught this is a current. Okay, how to this rod sliding along the inclined plane. There's also gravity present. We'll draw a plane diagram. This is a rod. This is that rod. Okay, fine. So what are the forces that will be acting here? Weight mg. Sorry, mg sine theta. Mg cos theta. normal contact. Then BIL force, how the current will flow. B bar into the plane. So B bar into the plane, what is the flux? Flux will be positive. Positive flux decreases d phi by dt negative. EMF induced positive. Then the induced current has to flow anti-clockwise. Then BIL force, how it will act here? So here you have to take like this. This is a rod. Current is into the plane and B bar like this. B bar current. So the BIL force will act here. So the BIL force here will act here. Then component of BIL cos theta. Here BIL sin theta, because this is theta and this is the acceleration. So MA equal to mg sin theta minus BL cos theta. What is acceleration? dV by dt. Then this moving rod will behave like a cell. Okay, fine. So then what is I is equal to? I equal to E by R. Then what is E? E actually will be like this. Huh? There's a rod, B bar like this, velocity like this. Then this will be theta. B cos theta, V sin theta. Which component will be responsible? Which component will be responsible? V cos theta. V cos theta will be perpendicular to the length. And do one thing. So the EMF induced will be, so what is I is equal to E by R. Substitute that value of I, BLV cos theta by R, L cos theta. Solving this, we'll get the velocity. Now we have the metal loop. It is entering the magnetic field. There will be EMF induced only in the regions, we'll give a number. Only the 1 to rod 1 to EMF will be induced. How much it is? BL V0. Then what is the induced current? How it will flow? Flux negative. Negative flux increases. d phi by dt negative. EMF induced positive. So the induced current will flow anti-clockwise. No EMF. Huh? By no EMF, flux constant. By no EMF, flux constant. By no EMF, because there is no field, no come for here in this region. What about the flux here? The flux is negative. Negative flux decreases. d phi by dt positive. EMF induced negative. Then the current should flow anti-clockwise. Okay, fine. So the direction of current will change. Next, we have to calculate the EMF induced. I'll give the dimensions of the side. So let this be L1, L2, L2. This is A, this is A, this is B. Then there'll be only, what is the loop? There's a loop. There's everything is a loop. Yellow color I'm shading, that will become loop. Then what is the area of this part of the loop will be? area of the bigger loop L1 plus there's a small gap. Huh? This gap will be small gap. In the bigger loop, so we can current is like a sir, how you do this one. So there's a bigger loop. Huh? EMF will be induced. This will be a smaller loop. EMF will be induced. Then the total circuit will be the bigger loop will be like this. The smaller loop will be like this. Then both the cases, what is the flux? Flux will be negative. Negative flux increasing d phi by negative. EMF induced positive. In both the cases, the cell will be like this. Then this you call E1, E2. Here will show like this. This will be E1. This will be E2. What is E1? E1 will be L1 plus 2L2 into B naught area. E2 will be this area. This area will be B into 2A into B naught. So definitely E1 greater than E2. So we'll determine the flow of current. This will determine the resultant current will flow like this. The outer edge will determine the flow of current. Similarly, come for this one. Here we have condition A greater than B. There will be EMF induced in this loop, and let lambda be the resistance per unit length. Then what is the flux? Flux will be negative. Negative flux increases d phi by negative. EMF induced positive. This E1. This E2. So this will be R. So how much of resistance will be lambda A, lambda A, the resistance per unit length, where lambda B, lambda B, lambda B, lambda B. We'll determine the flow of current, this flow, because E1 will be greater than E2. How much E1? E1 will be B naught into A square. E2 will be B naught B square. As A greater than B, E1 greater than E2. So this only will determine the flow of current. How the current will flow like this. Resultant current. Next we have situation motional EMF with varying magnetic field and moving rod. So EMF induced due to the net EMF induced due to the change in like a flux with the time plus with area. Two things are there. There will be EMF induced due to rate of change of flux, rate of change of area. There will be also EMF induced due to rate of change of magnetic field. So here we'll write like this. E equal to, we know flux is equal to, I'll do one thing. I'll proceed like this. Flux will be flux due to, like this will be B bar into S. Cos 0 it will become. B is what? B naught T. What is S? S is the area. And L is the length. We'll assume it. Then this will become L into X area. B naught L X T. I'll differentiate this one. D phi by dt. B naught L dt by dt. B naught L dx by dt into T. Like this, we'll get the EMF induced. This will be due to change in magnetic field. This will be due to the change in area, change in time. With the time, this is due to motional EMF. I'll write this separately. This is due to this EMF change in time. B, this is due to change in area. Okay, you may get situation like this, so take help of this condition. Okay, we have the motional EMF condition, so this will be t equal to 0, this is time t. The rod earlier was here, now it starts moving here. These are the fixed realm. Then what is the displacement of the rod in time t? X equal to v naught t. Then sum this y length. Then what is the area? Area will be 2 times of half into x into y. 2 get cancels. So x will be v naught t. Whatever the value of y, y will be y equal to x tan theta. X equal to how much? V naught t. Then flux equal to d into dA by dt. This is EMF induced, and how the current current will flow in this direction. Like this, different shaped loops also come. You should be careful. Now this rotating rod, rotation EMF. A rod will be rotated in uniform angle. Then what is the EMF induced? As the rod rotates, let me choose small element here. It will have the tangential velocity v at a distance x. Then what is the tangential speed? V equal to x omega. This is length dx. What is the EMF induced? dv dx. EMF induced across this small element, dv. What is v equal to? Tangential velocity. So this should be equal to x omega dx. EMF induced 0 to L. This is EMF in. So which end will be positive? Now here you assume a positive charge. The positive charge here will experience a force in this direction. So therefore the moving rod will behave like a cell. Sir, how to determine the terminal, which end will be positive, negative? You assume a positive charge inside the rod. The positive charge will have velocity. The positive charge will experience the magnetic force in the direction of magnetic force. The positive charge will drift. So the positive charges will get accumulated at end B, and the negative charges will get accumulated at end A. Like this, we can predict the polarity of. This is a rotational EMF. Then this is a rod. Now what is this? This is a semicircular wire. This is a semicircular wire. Then as it rotates, the EMF induced, effective EMF, how much it is? B omega L square by 2. What is this length? Let it be L. Where length AB is equal to L. Here also, what is effective length? Effective length is L. But sir, this semicircular wire, yes it is. This end will be positive, this will be negative. Irrespective of shape, here L means effective length. Similarly, this irregular shape. So what is the EMF induced here also? B omega L square by 2. Now I am rotating the ring. Then this of A, this is N B, COD. ACB will be a one cell. Then ADB also will be like a one cell. Net EMF induced will be B omega R square to R square. The radius will be R, no? So 0 to 2R. So this will be EMF induced. So net EMF induced in the loop will be 0. Because you come for plus C minus C will be 0. Net EMF induced will be 0. Fine, or the flux remains constant. Individual arc here EMF will be induced. So this will be positive, this will be negative. So flux constant, rate of change of flux 0. That's why EMF induced in the ring 0. We take the next one. Here I am moving this away from it. Let it be at a distance x. This L, side length L. Then we have to calculate the EMF induced in the loop. So we'll calculate the there will be EMF induced in this. So this altogether let me redraw that one. No, this will, you look at the other velocity like this. This particular side will be like a cell. EMF induced E1. No EMF induced in the side 1/4 because the velocity is parallel to it. There will be EMF induced in this rod. How much it is? E34. Infinity and infinity. So what about E1? E12. E12 equal to magnetic field. B1 2 into L into V. What is B1? Mu naught I 2 pi L plus X. So this is what the net EMF induced in the loop equal to E34 minus E12 because this EMF will be more than this one. Like this, see, to motional EMF idea very important in Faraday's law. What about the direction of induced current? Negative flux decreases, d phi by dt, positive EMF induced negative, the induced current will flow clockwise. What is I is equal to? That I is equal to EMF induced in the loop by resistance. We have a loop which is moving parallel to the rod. No EMF induced in the loop. Why no EMF induced in the loop? Because the flux will remain constant. How the B bar will be into the plane. So the flux will be constant. As flux is constant, no EMF will be induced. Next we have the induced electric field. This induced electric field. What is the meaning of induced electric field? We know like flux is equal to B bar dot H bar. Then d phi by dt equal to dB bar by dt into S or S dB bar. The angle between them, let it be 0. This is equal to EMF induced. Then further this EMF induced, there is a potential difference. This can be written as E bar dot dl bar. This is an expression for induced electric field. So now I want to calculate the electric field inside the let me calculate the electric field inside the solenoid. So what is this B bar? Who is producing this magnetic field? Solenoid. This is very, very important. You pass a variable current. Then what is the magnetic field produced by solenoid? Mu naught N I. If the current through solenoid varies, then definitely the magnetic field inside the solenoid varies. Then B equal to B naught T. We'll get like this. So here we'll get the magnetic field due to the solenoid. Then the magnetic field what happen will be varying with the time. The magnetic field varies with the time. Now, any charge kept inside the solenoid, will it experience any force? Okay, then that's what we are trying. So here, why did it experience force? Because an induced electric field is set up. How to calculate that one? We'll assume here dl small. How to get the direction of induced electric field? Flux will be negative. Negative flux decreases d phi by dt negative. EMF induced positive. So the induced electric field will be anti-clockwise. Then everywhere E bar and DL, it will be like this. Okay, fine. So what is the angle between E bar and DL? It is cos 0. So E into integral of DL. S what is S? Pi R. I ask what dB by dt is B naught. E into 2 pi R. This is a induced electric field. Then there is a point P1. There is a point P2. Then again to calculate there, again we'll assume a loop like this. What is S? S is here pi r square. Here we are assuming one more loop. Or I'll come for this one. E outside the field region. Better use will use separate diagram. This was earlier point one. Now point P2 is here. Now the diagram will be like this. No, this will be your R bar. How E bar? E bar will be like this. This one. So this will become S into what is the effective area now? Pi a square. The magnetic field region pi a square. Earlier pi r square. Now only the way the magnetic field is region that has to be taken into dB by dt B naught E into 2 pi r. So if you see the outside the solenoid also there will be induced electric field. And you have to draw a circle, then tangential to that everywhere the E bar will be. Okay, son, this is the short revision I have to do it. Now, what about the EMF induced in this particular loop? Find the induced EMF in the loop where the magnetic field is varying. So we have kept this loop in a solenoid. So there won't be any EMF induced in these rod. Why there won't be EMF induced? What are these arrows? Direction of E bar. Then what is the DL? DL will come like this. E bar will come. So EMF induced in the rod OA and OB. Why 0? Because E bar is perpendicular to DL. Similarly, you can write it as DL here. And now E bar like this. So no EMF induced in these rods, OA and OB. Okay, fine. What is the EDL? So this will become, so what is the cost? Yeah, DL cos theta. Theta will be 90 degree. That's why E will be 0. That's why no EMF induced in the rod OB and OA. Only in the rod AB it will be induced. Then I directly go for EMF induced in the loop is equal to EOA plus EOB plus EAB. EMF induced in the loop is how much? That will calculate area of cross section of the loop. Then this area of cross section will calculate. This is y, this is x, this is a. What is x is equal to root of a square minus y square. Area of cross section half into base 2x height y into dB by dt. 0 plus 0 EAB. dB by dt is x is how much? Okay, this is the EMF induced in the rod. These are some methods which you have to follow. Next, find EMF induced in the loop OAB. So here, again, no EMF will be induced in the, because the direction of E bar everywhere like this. Okay, fine. So there won't be any EMF induced in this loop. Why no EMF induced? E bar perpendicular. Again, no EMF induced in this side also. So no EMF induced in the side OA and OB. The reason E bar perpendicular to DL. Then EMF induced in the side, EMF induced in the loop is equal to EOA 0 plus 0 plus EAB. What is EMF induced in the loop? Area of the sector. S into dB by dt. S into B naught. What is S? Area of sector. Area of sector will be R square theta A square alpha by 2 into B naught into EAB. Problems related to induced electric field, it's a non-conservative in nature. Already I discussed in regular videos, go and check it in detail. Just a brief introduction I gave it. Then if any charged particle present here, will it experience any force? Yes, definitely. It will experience a force. Then if any charged particle present here, will experience a force. Okay, kids, now we have the inductance. It's a measure of opposition to the change in current. It's a measure of opposition to the change in current, to the varying current, or better say. Then let's assume that. So practically the inductor will have its physical length L, and this will be the axis. We'll call this as axis of inductor. It's nothing but solenoid only. This is length. Number of turns. Then we define some quantity called a number of turns per unit length. So property of inductance. Now let's assume that I'm going to send the array increasing current. I naught T square. Then the magnetic field here will be B like this. Then this is equal to number of turns. We know the magnetic field inside the solenoid will be mu naught Ni, where N will be number of turns. Then if the current increases, the magnetic field will increase. Then you are standing here. Then according to this condition, what is the flux? Flux will be positive. Positive flux increases. d phi by dt positive. EMF induced negative. Then EMF induced negative means how the current should flow. d phi by EMF induced negative. Current should flow clockwise here. So this person will see that the current will flow clockwise. So clockwise current will show like this. This is induced current. Okay, then this inductor will push it. So here will represent like this here. This is the inductor. The induced current then here actual current I. We'll see how the induced current will flow. Now here I'll take the something decreasing current where t greater than 0. So with the time the current will decrease. Again how the B bar will be produced in this direction. Then the person standing here, for him, what is the flux? Flux will be positive. Positive flux decreases. d phi by dt will be positive. EMF induced, sorry, flux is positive and the positive flux decreases. d phi by negative. EMF induced positive. Positive means how the current will flow anti-clockwise. This for this person anti-clockwise. So here decreasing current, here increasing current. Here decreasing current. Then how do the induced current? The induced current will flow now in the direction of actual current. So how the polarity? The polarity should change here now. Here the polarity will change like this. So this will be positive, negative. This will be negative, positive. Where E equal to. So there's a basic idea. Then how to what is the basic idea? How to you can see the flux linking is directly proportional to the current here. To remove this proportionality, we'll introduce a quantity self-inductance. So the self-inductance of coil will be flux linking the coil to the current through it. What the flux is equal to? Number of turns into B into S. What is further? B mu naught Ni, magnetic field due to solenoid. N mu naught N Ls. So there's a magnetic field, this one. So mu naught N square V, where V will become the volume. 1L just here, I'll bring like this. This further simplification. So this will be the self-inductance. Okay, like this we'll calculate this will be the actual current flows like this. Actual current flows like this. How the induced current will flow in the direction of actual current because current is decreasing. If increasing current is flowing in this direction, then the induced current will flow here. So what is this coil? If current through the coil increases, the coil will try to decrease it. If current through the coil decreases, the coil will try to increase current. So what actually this coil is doing now, it is opposing the rate of change of current. If a constant current flows, no self-inductance. So why do self-inductance will come? Due to rate of change of like current here. So therefore now this particular thing, we know phi is equal to Li. This will be d phi by dt equal to L di by dt. This is equal to minus C. This is EMF induced. So self-inductance, you can define it like the unit for self-inductance will be 1 Ng. When you can say 1 Ng, when a current through the coil varies at a rate 1 ampere per second, then EMF induced is 1 volt. Okay, like this we'll define this as the self-inductance. Okay, now like how to write KVL, the current through the coil is increasing at a rate 0.4 ampere per second EMF, and the current is 2 ampere. The charge here will be plus Q, minus Q, plus minus, plus minus. Then we'll write the potential difference A and B. Okay, fine. So this will be VA minus where the current enters positive, where it leaves that is negative. So this will become, I'll treat this current element, inductor as current element, minus C, minus IR, minus Q by C, minus VB, DI by dt. Current is increasing, so therefore we have to put that as positive. VA 2 into 0.4 minus 4, 2 into 3 minus Q by 3 minus will be 0. If I say Q equal to 2 coulomb, substitute, we'll get this one. Or you can replace this with a cell. EMF induced will be 0.8 volt. This is 4 volt. This is 3 ohm. This is a capacitor. This one is an inductor. Where all inductor is there, you are replaced. So when to replace with a cell, it's left to you that one. If you are treating current element, substitute di by dt with sun. Current increasing positive, current decreasing negative. Then if it is treating like a cell, then if current increases, then the positive terminal, the current should enter positive terminal of the inductor, this end. So this is one basic method. So where all KVL comes, so you have to use this method. Okay, now we are discussing the growth of current in RL circuit at t equals 0. Okay, we have switched on the circuit. Then the current in the circuit, it will flow like this. I plus minus. Here drop VR. This will be VL. So here applying KVL, E minus IR minus VL equal to 0. then IR L di by dt. The current in the circuit will increase. So integrating and substituting, we'll get the value this as P by lambda, where lambda is called as time constant. Time constant of circuit. The unit for this will be in seconds. This is a growth of current. So with the time, initially at t equals 0, at t equals 0, the inductor will behave like a open circuit. At t equal to infinity, the inductor will behave like a short circuit. And this is steady state current, which is equal to E by R. Then how much of energy is stored in inductor? L I infinity square by 2. This energy is stored in the inductor, half L I square. Then at t equal to infinity or steady state, it will behave like a open short circuit. So the drop across inductor will keep on decrease. Okay, this is about the growth of current. At steady state, it will be like short circuit. At t equals 0, open circuit. Then we'll go for decay. At steady state, the energy in the inductor will be given by L I infinity whole square, which is equal to L E square by 2R square. Then I'll move the switch from 1 to 2. When we move the switch from position 1 to 2, then there won't be cell to provide this EMF to support this magnetic field. Then the flux starts collapsing. Then according to the Lenz law, the induced EMF should be such that it should flow in same direction. Suppose earlier there's a loop. There's one loop we are considering. This one. What was the direction of this I infinity? Then how the magnetic field will be in this direction. Then the moment switch is moved from 1 to 2, there won't be cell to support this current. Because of no support of current, the magnetic field will be mu naught N I. As the current starts collapsing, the magnetic field also starts collapsing. Then as the magnetic field starts collapsing, then definitely what will happen to the flux? Flux will collapse. Now the flux linking the coils, each turn of the coil will be varying. So due to that, EMF will be induced. So according to the concept, flux is negative because B bar, we are assuming some person, let it stand here. B bar will be in this direction. Okay, fine. B bar, flux will be negative. Negative flux increases d phi by dt. Negative. EMF induced. Positive. Positive means how the induced current should flow. Negative flux decreases d phi by dt positive. EMF induced negative. Then the induced current should also flow in same direction. That induced current I'll call I decay. Okay, fine. So therefore, the moment you move the switch from 1 to 2, a new current will flow. That will call induced current or decay current. Okay, and this decay current will start flowing like this. Then the drop across the inductors equal to drop across resistor. So the current is decreasing equal to I into R. Solving this will get I infinity e to power of minus t by lambda L by R. This is expression for decay current. By negative sign, the current decreases. So this is a decay of current in LR circuit. So all the energy in the inductor now will be lost across the resistor. This is a basic condition. At steady state, we have to calculate current. Find current at steady state. So this is the current I, this is I2, this is I1. Here current I, this is I2, this is I1. Then at steady state, how the inductor will behave like a short circuit. The inductor will behave like a short circuit. Then where all inductor is there, we should replace with a short circuit. Okay, fine. So what is I1? I1 will become equal to E by R1. I2 equal to E by R2. Then at T equal to infinite, again find the current at steady state, the same thing here also. Then at any instant, the drop across the inductor must be equal. So therefore, L1 di1 by dt is equal to L2 di2 by dt. L1 di1, L2 di2. 0 to I1, 0 to I2. So let the current and after long time it will be like a short circuit. Both inductor so what is I is equal to E by R. So I is equal to I1 plus I2. Substitute this I equal to I1, I2 will be L1, I1 by L2. Similarly, I2 will be like this. Where all inductor is there, you have to replace with a short circuit. These are the problems. Simple, which will be very useful for you in exam. Now we have to calculate the find currents I1 and I2 at time t. So this will become like a RC circuit. So I1 is equal to E by R1 e to power of minus t by lambda 1. What is lambda 1? RC. Time constant of circuit. Similarly, what is I2 equal to? E to power of minus t lambda 2, where lambda 2 equal to LR2. This is a time constant of the circuit for LR circuit, time constant for RC circuit. Like this, you can individually treat RC circuit one and RL circuit is other one. We have to calculate the current through the cell at t equals 0 and t equals to infinity. At t equals 0, where all capacitor should be short circuit and inductor should be open circuit. So we'll draw the basic circuit. the inductor will be open circuit. Capacitor will be short circuit. Here the inductor short circuit. Capacitor will be, sorry, inductor open circuit. Capacitor will be short circuit. So the current will take path like this: I, 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 and I. Okay, there's a resistance R, 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 here capacitance C, L, L and C. So the path will be like this. So the current will flow like this. This is a path. What is I is equal to? I is equal to now E by 2R. At T equal to infinity. At T equal to infinity again. Capacitor will be open circuit. Inductor will be short circuit. Inductor short circuit. Capacitor open circuit. Then how the current will take path like this. Then also current at T equal to infinity, how much it will be? I. Next we have the inductors in series and aiding each other. Means the direction of flux or the direction of B bar in both the inductors will be same, or the current will flow in the same sense in both the coils. Then the effective inductance is given by L equal to L1 plus L2 plus 2M, where M is called as mutual inductance, which is given by K into L1, L2. K is called as coefficient of coupling. This value will be coefficient of coupling. Here the B bar in both the inductors will be in same sense, or in sense the current in both the coils will flow in same sense. The current in both the coils, if they flow in different sense, then the effective inductance is given by minus 2M, where M is coefficient of coupling. Where M is the mutual inductance, K is the coefficient of coupling. K depends on separation between the coils and the medium between them also. This is about the inductors series parallel. If the separation is far away, K will become 0, then inductance will become L1 plus L2. Current in if the current in inductors flow in opposite sense, the effective inductance this one. If the current in both the coils flow in same sense, there is a formula. Similarly, for parallel, so we have like this. There's some generalized thinking. Derivations at this point very lengthy, so I'll be writing only the formulas. So when they are supporting each other, the effective inductance L1 L2 by L1 plus L2 minus M square minus 2M. Okay, this is the effective inductance. M is the mutual inductance. Then the self-inductance here L1, L2 by, when they are opposing, will be minus M square L1 plus L2 plus 2M. Okay, fine. So this will be the parallel aiding inductors, parallel opposing inductors. Now formulas you have to remember, very important. Where M is the mutual inductance between the coils. A lot of data is there in this chapter. You have to remember, there's no other way. You revise, read many number of times. Definitely, all this will become memory. Though you understand, you'll forget. The reason you are not read many times. You read many number of times, it will become memory. No. Let's assume that a current I1 is flowing. Let N1 be the number of turns. Here N2. This is the axis, axis of both the rings. There are two rings are there, ring A and ring B. Okay, fine. Huh? Now current I1 is flowing. It will produce here magnetic field in this direction called B1. So here you are standing at this point. Then what is the expression for B1? B1 will be mu naught N1 A square by A square plus X square to the power of 2 by 2. Then the flux linking it equal to B1 into pi B square. Okay, this will become the number of turns here N2. So then this will substitute here mu naught N1 A square pi B square N2 then the mutual inductance we define like this, mutual inductance. Flux linking second coil to the current in first coil. Or will differentiate this rate of change of flux induced EMF in second coil due to rate of change of current in the first coil. Either of the formula you can use it here. So therefore, what is the mutual inductance? Flux linking the second coil to the current in the first coil will be mu naught N1 N2 pi A square B square to the power of 3 by 2. Okay, like this we'll get the flux mutual inductance between the coils. Right? So similarly, if the two coils are there, coplanar, if they are coplanar, earlier they were coaxial. If they are coplanar, then what conditions will come? Number of turns N1, let this be N2. Let the current I flow, mutual inductance between them, where A will be very small compared to B. Okay, I think let me draw that one. A will be very small. Okay. So then magnetic field B1 is equal to B2 is equal to mu naught N2 mu naught N I2 by 2B. Flux linking the inner coil should be equal to N1 into B2 pi A square. N1 B2. B2 is how much magnetic field? Mu naught N2 I2 by 2B pi A square. Mutual inductance, flux linking the first coil to the current in second coil. Mu naught N1 N2 pi A square by 2B. Okay, fine. Like this we define the mutual inductance between the coplanar coils. It is. Earlier coaxial coils. We have next the LC oscillations. Initially, a charged capacitor will be connected to like a inductor with zero energy. I'll close the switch. This is at higher potential, lower potential. The current starts flowing here. The current will flow like this. Then at one instant, all the energy will be there across the inductor. Here, all the energy was there in the form of electrostatic field in the capacitor. Now, all the energy will be there in the inductor. Now, according to the Lenz law, there won't be current to support this magnetic field. The magnetic field starts collapsing. According to Lenz, the current will flow in same direction. Now, the current starts flowing in same direction. Then, finally, what happened? Here, all the energy will be there in the capacitor. Again, the capacitor starts discharging. Now, the current now will flow in opposite direction. Then at one instant, all the energy now will be available in the inductor. Here, all the energy will be available in the inductor. Again, the inductor will happen. There won't be potential difference across the capacitor to support the current. There won't be current. Then the flux starts collapsing and the current will flow in this direction. Then all the energy will come across the capacitor. So like that, oscillations are set up. Look at the current flows clockwise, anti-clockwise. Then applying the KVL, we'll get plus Q by C minus L di by dt or plus L di by dt equal to 0. Q by C plus L so Q by LC plus so comparing with this omega square equal to 1 by LC. T equal to 2 pi by omega. T equal to 2 pi omega equal to this much. Omega square Q it will be. Omega square is this much. So T equal to 2 pi by omega. Omega will be 2 pi by T. Two pi by root LC. Now the time period of oscillations is given by 2 pi root of LC. Now the frequency is given by 1 by 2 pi root of LC. May not be very important topic. Just have the awareness. Then from the conservation of energy principle, Q naught square by 2C is equal to the initial energy in the circuit should be equal to energy in the circuit at any time t. Li square by 2, Q square by 2C. Then the charge will oscillate. Then the current, then the formula will be like V equal to this I is equal to omega Q naught square by Q square. V equal to omega root of A square minus A square. The same thing in SHM formulas are there. Charge displacement, velocity will be current and rate of change of current will be acceleration. There is one basic condition which you have to remember. This will be the oscillation energy. Whether sine or cos will determine initial conditions. This is a small conceptual topic. This iron plate, I'll make it to move. As I start making this iron plate to move, as it is entering, when it is entering, there will be an EMF will be induced. There will be EMF induced. So the way the EMF will be induced, The flux linking the plate will change, and because of this, the induced current start flowing here. And why do this induced current? Why do they flow in random path? Because like it's a conductor, no? The free electrons, according to the Lenz law, they'll flow in anti-clockwise direction. Only in this region they'll be flowing here. Or nothing but if I take the some conducting disc, let this be a conducting disc. I'll introduce here a varying magnetic field. And because of this, the induced current, they'll not flow in one particular loop, random direction in a closed path. Why do? Because the free electrons which are present in the conductor, they'll move because of that induced electric field. These are called as eddy currents. The currents that will flow in the conducting sheet, not conducting loop. This is a metal disc. Okay, fine. Now on the same slice, if I make it to move, I'll slice it. Then this particular plate, I'll make it to move. As I'm moving, when I'm moving this one, so definitely here what will happen? The eddy currents are not permitted to complete the path. So here definitely very less eddy currents will be flowing compared to that one. Here the eddy currents will be more. So definitely a resistive force will act here, Fr2. Here Fr1. Some external force is applied. Here external force is applied. Fr2 will be less than Fr1. Here the resistive force will be very less because less number of eddy currents will flow. Here eddy currents will be more. In eddy current, somewhere it is a very good for application. In some applications, it's like a necessary evil. So it should be minimized. In some applications, we need eddy currents. So there's one basic idea. Okay, kids, this is about the electromagnetic induction.